If we analyze this more carefully, and what I've done here is I've stretched out the time scale, we see our drive signal here. And so if we measure the time between the drive signal and the received signal, so it's 1, 2, 3, 4, 5, 6, 7 units, 7 times 200 milliseconds, microseconds per division is 1400 microseconds or 1.4 milliseconds. So if I multiply the speed of sound in water, which is 1484 meters per second, by the time delay there, 1.4 milliseconds, I get about 2.05, 2.07 meters, which is exactly what I would expect. That's my spacing between the two transducers. Now let's look at the reflected signal. So I've reduced the time scale again. Here's the start of our drive signal, and here is the start of our reflected signal. So it's 1, 2, 3, 4.2 divisions times 1 microsecond per division. So that's 4.2 microseconds time delay. If you multiply that by the speed of sound in water, you get a little over 6 meters. Well, there's no surprise there, because what's happening is the sound leaves the transmitter, gets to the receiver, bounces off the face of the receiver, goes back to the transmitter, bounces off the face of the transmitter, and then goes back to the receiver. So that's 3 path lengths, each one being 2 meters, for a total of 6 meters, which is exactly equivalent to the time delay that we see here between the transmitted signal and the first reflected signal. So the 1.4 millisecond time delay that you see between the transmitted signal and the received signal is exactly what you would expect for a 2-meter separation between the transducers. The 4.2 millisecond time delay that you see is exactly what you would expect from a reflection. So what's happening is the sound is leaving the transmitter, it hits the receiver. Because the receiver has such a big surface area, it reflects sound back to the transmitter. The transmitter also has a surface about this big, so that sound reflects and comes back to the transmitter. So that's 3 path lengths, which is 6 meters, which exactly corresponds to that 4.2 millisecond time delay. It is possible to get other reflections. The most common would be a reflection off the surface of the water. And it is plausible that sound can go up from the transmitter, hit the surface of the water, and then bounce back down to the receiver. However, that's not a problem here, and the reason is because the large diameter of these transducers and the very high operating frequency from 50 kilohertz to 100 kilohertz means that there's a very narrow beam pattern coming out of these transducers, a very narrow lobe. And what that means is that that lobe is just not wide enough for the sound to be able to go up to the surface, or as far as the receiver is concerned, to even be able to pick up anything that's coming down at an angle like this from the surface. So let's look at our data on the Stanford Research Analyzer. The bottom is just like an oscilloscope trace. It's voltage versus time. And the top trace is the FFT analysis of our chirp signal, the signal coming in from the receiver. So what you see here, I've exaggerated the scale, the vertical scale here, so that you can see the first signal from the receiver and the reflected signal. Now, in this case, the reflected signal is showing up before the first signal because I only have a 2 millisecond time window here. So the reflected signal from this chirp is way out here to the right. I can, using the delay, I can move that window around. So if I move my first received signal to the left here, what you see is that because the first reflected signal is 4.2 milliseconds out, I can't get it in there to show it to you. But because this is repeating, I can get the reflected signal from the previous chirp. So that's why I move it to the right, and so here is a reflection. And what you'll see, if you look at the trace carefully here, you'll see that it's not really smooth. There's a lot of little dips and valleys here, or kind of a ripple. And that's a result of measuring our first signal and our reflected signal. If I move the window so that only my first received signal, my first signal from the transmitter is being measured, then you see that the curve here is much smoother. And I'll go ahead and auto scale the bottom display so that you can see the chirp better.